and welcome to the Supercharge performance session. We're going to talk about GPUs today. How many of you have used GPUs in a data center before? Raise your hand. Oh, quite a few. That's good. How many in the cloud? Have used them in the cloud before? Okay, so some of you have had the fun experience of setting up your own GPUs, and some have had the experience of spinning them up and just using them remotely. So we're going to talk about why people are interested in GPUs, and we're going to tell you about how GPUs are available in Google Compute Engine, and remind you why you should be so happy about it. And anyone that's set up GPUs before should know that already. And then I'll walk you through how you provision a GPU instance. But the highlight of our talk today will be 3 demonstrations. One from MapD, who will be showing amazing data analytics, very fast data analytics using GPUs in the cloud. And then Schlumberger is going to talk about how they do seismic high-performance computing with GPUs in Google Cloud. And then we'll talk about remote workstations. So why don't we get started? So this must be familiar to most of you. If you've done much scientific or engineering work or work in machine learning, you know, a lot of that requires matrix operations. And these matrices can be very large, sometimes, 1,000 by 1,000 or larger. And the nice thing about GPUs is they can do some of these operations in parallel. So for instance, multiplying AX in order to get B, each individual element of A can be multiplied by an element of X in parallel, independently of all the other ones. But of course, then you have to gather up some of that information, not quite as parallel when it comes time to add those together, but still very parallel. And the nice thing about GPUs is they have a lot of cores for doing these operations in parallel. So just a quick overview, CPUs typically have on the order of dozens of threads that can do these operations simultaneously, but GPUs have, in some cases, 2 orders of magnitude, 100 times as many, and so they can do these calculations simultaneously. And the other thing that's nice about GPUs is they have lots of memory bandwidth, sometimes an order of magnitude additional memory bandwidth. So if you have a lot of data to churn through, you can push data through very quickly through those cores. So I have a little animation to show you how that works. A CPU is very flexible, can do lots of different types of operations on the data that flows through, and it can scale up to dozens of cores simultaneously. So you can crank a lot of data through a CPU. A GPU has higher memory bandwidth, so it can push some data through, streaming data through more quickly, and then can scale up to thousands of cores simultaneously. So you can imagine if you have lots of operations to do, you can do a lot more work all at once. So one example of that is AMBER molecular dynamics software, where you can do a simulation of the interaction of molecules together. And this chart shows you that in some cases using CPU nodes, up to 100 CPU nodes, 48 2-processor CPU nodes, you can get up to around 20 nanoseconds of simulation per day. So 20 nanoseconds every day. It takes a lot of days to get up to a single day of simulation. With the GPU, you get 2.5 times that performance with 3 nodes of 4 GPUs. And NVIDIA was kind enough to share some data with us, our partner. They have mentioned that GPU developer interest is increasing substantially. We have over 3 times as many developers signed up now in the past 2 years, up to 400,000, and more than 20,000 organizations engaged with NVIDIA for deep learning activities. And you can see that the major deep learning frameworks are all GPU enabled now, accelerated by GPUs. So, what are the things you can do with the GPU? Raise your hand if you've done some of these things. Machine learning. Who's done machine learning? So a good number of group. Frame rendering, image composition. A few people here. Physical simulation, analysis, FEM. Few people. Real-time visual analytics on an SQL database. You'll see that one today. We're going to show a demo. How about faster than real-time 4K video encoding or transcoding? Yeah, we got someone here that's excited about that. Sequence mapping and alignment, or subsurface analysis for the oil and gas industry. I should see some hands from Schlumberger over here. They'll be talking about that later. So just to give you some examples, we're going to be talking about V-Ray today, where we have more than 100 K80 GPUs. That would be on the order of 500 teraflops of performance, rendering massive models in real time. And then we're going to show a demo of MapD's real-time visual analytics, where they use the parallel processing power and high memory bandwidth of the GPU to query billions of rows at a time. And I like to highlight this quote, which is also on our webpage, that a single HiMem 32 instance with 8 GPUs was almost 100 times faster, 85 times faster than Impala running on a cluster of 6 CPU nodes. So that's an example of real value. So as you know, we have K80s available today in beta. We've announced and will soon deliver S9300s from AMD and NVIDIA Tesla P100s. A lot of enthusiasm for the P100s coming out. And right now they're available in the US, Europe, and Asia. And this, as I mentioned before, offers teraflops of performance per instance, and especially for machine learning, engineering simulations, and molecular modeling. You can attach, as I mentioned, also 8 GPUs per virtual machine, and you can do either 1, 2, 4, or 8 simultaneously. We have them in 3 regions today, and then we have another region, US West, coming online within the next few weeks. One thing that people really like about the GPUs in Google Cloud is that we offer essentially bare metal performance. We're offering them through pass-through mode, which means they're directly attached to the CPU that your VM is running on. So it's directly attached, you get high performance, and you can attach GPUs to any machine type, so you have a lot of flexibility as well. And since we charge only per minute with a 10-minute minimum, you can choose a GPU that best fits your wallet and also pay only for what you use. You don't have to worry so much about if you're using it for a full hour or a fraction of an hour. And then you don't have to make a capital investment too, which is a huge advantage. I think pricing is available online, but I thought I'd mention it here, that it's 70 cents per GPU per hour for the K80s in the US, and then Europe and Asia are each 77 cents per hour per GPU. Now, here's the nice thing is, again, people raised their hand earlier. If you've installed a GPU before, you know it's a lot of work to do that, buying the hardware, waiting for it to arrive, buying the system that surrounds that, the networking, putting it all together, assembling it. It doesn't work the first time. Why is that? You know, is the GPU bad? Did I seat the card correctly in the board? It's really a lot of, it's a challenge, and you have to have the physical space. And the other thing is, you know, hardware does fail. Who manages the fleet to make sure the hardware fails, it gets replaced and fixed? But I think one of the biggest things is power and cooling. So if you're thinking about running 100 GPUs somewhere, those GPUs put out a lot of heat into your data center, right, or into the closet you're putting them in. And so you have to be careful, or you might install more GPUs than your cooling system can handle and actually not be able to run them at the high performance. But we've taken care of that for you. So if you use GPUs in the cloud, you don't have to worry about any of these things. Just to step you through what it takes to provision a GPU in the cloud, I was going to suggest that someone get out their computer and start putting together a GPU machine right now. You can start ordering online to order a GPU and see how long it takes you. In the meantime, we'll have a race. We'll see how quickly we can get one up in the cloud. I think I'm going to win. So you go to the GPU, to the console, and you choose the Compute Engine tab and click on the Create Instance button. And then you can choose Customize. That's where the GPUs are hidden right now. Once you choose Customize, you'll see that you can choose the number of cores and how much memory you want, and there's a little GPU link you can click on underneath. And you can choose the number of GPUs you want and the type. Of course, the type right now is the K80. And the number, you can choose 1, 2, 4, or 8, as I mentioned before. Now, if you prefer to use the command line, here's an example command line for provisioning a GPU instance. And the main thing to pay attention to is the accelerator option with type and count to say what you want. So either one will get you a GPU. Now, I want to mention, too, GPUs don't support live migration. Because we're offering them in pass-through mode to get the high performance, we don't actually have the capacity to capture the information in the GPU, the current state of the GPU in the memory, and move that over to another physical GPU. So when it's time for maintenance, we notify you, give you 1 hour notification, and the GPU terminates 1 hour after we give you the notification. And you can, we'll give you some support for that. If you watch the VM metadata, you can see that if you run this command, you'll get a none if maintenance is not scheduled, or you'll get a timestamp that says when the maintenance is going to happen. And so based on that timestamp, you can either reboot right away and get a new machine, or you can checkpoint what you're working on, save it, and bring it back up in a new instance. And I should have mentioned that the information about how to do that is online in this link. And then if you're using TensorFlow, we make it even easier. You can use TensorFlow Supervisor, and that allows you to manage banks of GPU-based VMs, and it handles both shutdowns and crashes cleanly, easily resumes, so you don't lose any data. Because especially when you're doing machine learning training, it might run for weeks at a time, and you don't want to lose your work due to a maintenance event. So now I'd like to invite Todd up on the stage to give a demonstration, introduce himself, and give a demonstration.
Thanks, John. Hey, everyone. Really excited to be here today. Tell you a little bit about MapD, which is a GPU-accelerated database and visual analytics platform. And we'd really like to thank John and the Google Cloud team. We're tremendously excited about what Google is bringing to market here in terms of their GPU instances. There's a lot of flexibility for developers. There's a lot of flexibility for startups like us to basically mix and match components and deliver the perfect system. So just a little bit about us. We are a Series A startup, have some great investors, including Google, as well as NVIDIA. We've won some awards. We were Gartner Cool Vendor last year, and have had a good set of early customers, including Verizon Wireless, who I'll be speaking with at Strata next week. So everybody knows that organizations are awash in data. So they're saying that data growth is actually 40% year over year for your average organization. And storage is not the issue, right? So people can put the data on disk. They're building massive data lakes, massive Hadoop clusters. Storage is not the issue. The issue is when you actually want to analyze this data. So if data is growing at a 40% year-over-year rate, compute or CPU compute is actually only growing at a 20% year-over-year rate. And so this compute gap between the growth in data and the growth in CPU is causing people to do all sorts of unnatural things. People downsample, people pre-aggregate, people basically have to deploy huge scale-out clusters of hundreds, if not thousands of nodes with diminishing returns of scale. And so people are at this impasse. And that's where GPUs come in. So I don't want to reiterate what John has said, but GPUs are not only fast, but their processing power is growing at a tremendous rate. And not only is it keeping up with the growth in data, but it's actually surpassing it. So whether you measure by compute bandwidth or by memory bandwidth, you have a huge amount of throughput on GPUs. And I'd like to point out that everybody pays attention to flops, and certainly GPUs deliver there. Actually, if you look at the memory bandwidth, that's almost more important for data analytics problems, where things are often memory bandwidth bound. So that's where MapD comes in. So MapD was built from the ground up to leverage the massive parallelism and memory bandwidth of these graphics processing units to literally deliver 100 plus X speedups over CPU systems on an equal hardware cost basis. Going back to that quote that John showed earlier, comparing us to Impala. And so you can run these crazy fast SQL queries over billions of rows, sub-second, allowing for the first time truly interactive exploration of big data sets. And because one of the killer use cases is so often slice and dice visual analytics, we built MapD Immerse, which is a web-based visual analytics engine, which not only leverages the speed of these GPUs, but the ability of the GPUs to render graphics. So we sort of use it as a 1-2 punch where we can run the SQL query over billions of rows, and because you often don't want to actually transmit all that data back to the client, we can actually render it in situ right on the GPUs using the graphics processing pipeline and render it in place and send back a compressed PNG. So with that, I'm going to cut to a quick demo here. Okay, can everybody see my screen? Great, so this is a relatively sizable data set. This is 2 billion records. Basically all the SHIP AIS or SHIP transponder data from throughout 2015. What's notable here is that we're running on a single 8 K80 or 8 GPU, 4 K80 Google compute instance. So if you tried to imagine the amount of compute you need to bring to bear to allow interactive querying on this data set on a CPU cluster, it's pretty amazing we're doing this on a single node. So you'll see all kinds of different metrics here, number of unique ships, histogram of vessel length, destinations. Here's actually the ship ID, so we can drill down to an individual ship. Speed, vessel type, time. And then last off, you have this map, which is actually all the points color-coded by the vessel type. So this is an example of MapD's backend rendering capability, what we call our Iris rendering engine. You wouldn't want to actually send 2 billion records from your server to your client, so we actually render and rasterize that on our backend on top of the SQL query, almost as a visual UDF, and then spit out a PNG, an interactive PNG to the client. So the cool thing here is that actually, as I zoom in here, you're going to notice that basically, I'm going to go into the Bay Area. Everything updates in real time. And actually, each one of these charts is hitting the back end with a query that's probably responding in about 30 or 40 milliseconds. And that's why we can be so interactive, even at this scale, even on a single node, because we're leveraging the power of these GPUs to basically brute force these queries and answer them in a fraction of the time you could on a CPU-based system. So as I zoom in here, I can look, what if I actually wanted to see the fastest vessels? So I'm going to kind of cross-filter here and look at number of records here where people are going at about 20 knots. And then I can see all these records. I'll notice first off that if I increase this even farther, most of the fastest boats are actually passenger boats. So I could drill down into that and we'll see these passenger boats, and then I could actually find an individual boat here and drill down, and actually we could even zoom in and see their exact tracks across the Bay Area here. So it's a pretty fun data set, and you can again get very granular. So if we actually go off and look basically out into the bay, you can actually see where the tankers sit, and they circle here and they moor, which is pretty cool. I'm going to quickly show you one other thing. How am I doing on time? Let's see. Okay, just 2 more minutes. So we not only built MapD, or our immersed visual analytics platform, to be fast, but we also built it to be very easy to use. So what if I wanted to explore the relationship between speed? Let's see here. I'm going to go to a scatter plot. What if we wanted to look at the relationship between vessel length, and we'll put that on the x-axis, and speed, which is SOG here. So we immediately have the scatter plot, and again, this is actually leveraging the power of the GPUs to do this on the back end. And here, for good measure, I'm actually going to color by the type of boat. So immediately here, you can see that the kind of the bigger the boat gets, the longer the boat gets, the faster it goes, except the smaller boats, the slow ones are the tugboats here, but the longer ones are passenger and other types of ships. So I could easily build on this. If I wanted to, I could add another chart and cross-filter. But it's very interactive and easy to use. And this kind of interactive data exploration at scale is something that MapD really excels at. So thank you. Thanks, John.
Hello. Hi, everyone. I'm Kanai Pathak. I'm from Schlumberger. How many of you attended the keynote speaker speech this morning? All right, quite a few. So you heard our CTO, Mr. Ashok Belani, talk about the high-performance computing work in oil field and our history of using CPUs and GPUs. And so we're going to talk about how we are using now GPUs in cloud. And thank you, John, and thank you, Google. It has been an exciting journey so far, and we're just getting warmed up. So all right, so Schlumberger, very briefly, what do? We provide insight into subsurface, everything below the earth and the layers and structures and where the hydrocarbons are. This is a set of services that we provide to our customer. We are a technology company, and so high-performance computing especially is quite relevant to our one service that I'm going to talk about today is the oil exploration, and we call it seismic processing, seismic acquisition. All right, what's interesting for us as computer scientists is the volume of data that we acquire, volume of data that we need to process, and for that we have massive high-performance computing centers around the world just dedicated for seismic processing. These centers have been, they have everything from building to power cooling space to CPUs, GPUs, storage, and we've been doing that for quite a number of years. quite successfully. So you can look at the volumes of the amount of data that we acquire and amount of data that we have to process. It requires, a lot of computing power. And let me talk about the seismic exploration in a very brief 2 steps. Step number 1, we acquire data. And as you can see, we acquire a large amount of data per job or per project. And we cover kilometers and kilometers, square kilometers of area around the globe. The step number 2 is to process them, to build this subsurface understanding what's really going on down there. That requires massive amount of computing, millions of cores, millions of millions of threads and GPUs. And it is the classic high-performance computing that we've been doing for many years. So the question we started asking ourselves a couple of years ago, and prior to that, perhaps a little bit, can we do this massive parallel computing in cloud effectively for business? Can we do it for all the workflows that we need to do with seismic, not just 1 or 2 algorithms? And the answer is, today, yes, we are doing commercial work in Google Cloud using compute engine with GPU. Without that, it would not have been possible. How do we do this? I'm going to invite my colleague, Carlos, to talk about that. Thank you.
Thank you, Kanai. All right, so how do we do seismic processing? We have strong requirements on dynamic resource allocation, data management, and fault tolerance. This is because of the nature of our business, the way we do processing, right? And because of these requirements, we try to avoid using MPI or most of the classic HPC, high-performance computing frameworks. So a few years back, we built our own software stack for our own data centers. And that stack provides a MapReduce-like kind of infrastructure that introduced sufficient amounts of fault tolerance and dynamic resource management. And it contains, so for doing this, it basically has its own custom job scheduler and custom resource and data management layers. As we brought that software stack that we built for our own data centers into the cloud, some things were familiar, like, for instance, the NVIDIA K80s, right, which provided great performance per dollar. And other things were essentially opportunities. So some of those opportunities were the ability to dynamically create instances, dynamically adapt the VM's characteristics to match the performance requirements of the jobs. And some of those were like, for instance, the needs for monitoring and control were a opportunity disguised as a challenge, right? So in the graph here, you will notice, I know you can't quite read the details, but you'll notice there are 3 main layers on this, right? On the top layer, you have a very small number of nodes, which contain what I call the durable infrastructure, right? These are the pieces that make the virtual data center work. It's a small number of nodes, like the job controller. Now, the middle layer is the bulk of the data center. It's the bulk of, are the compute nodes. These are what we call the ephemeral infrastructure, and they're basically live for the length of a job. You create those nodes on demand, sized and dimensioned for what your job needs. And the bottom of the layer is basically composed of a parallel file system that feeds the data through those to the compute nodes, and has a life cycle that is independent of the other 2 layers. Now, finally, what we have is we call it a FAT link. It's a 20 GB link between our data center in Houston and Google data centers. And that allows us to basically upload, well, move the data, the massive amounts of data that we have between Houston and, well, between our data center and Google, right? And when I say a massive amount of data, basically a job commonly requires 60 to 100 terabytes of input data to start running. So to give you an example, in this case here, we have a single imaging job. So this is running reverse time migration and lasts for a few days. We ran it last weekend. This was probably about 3 days. And as you can see in the curve here on your right, on your left, it starts with 20 nodes, and it acquires nodes as it scales up. So at its peak, it has a little bit more than 1,700 nodes, and then it ramps down as it finishes the work to be done, right? So I really get excited about this kind of problem because of the massive scale of these computations. So at the peak, we are using about 7,000 GPUs, and we are using something around 20,000 CPUs for that single job. Now, this is not the only job that we're running, right? And oh, and by the way, we were generating about 220 gigabytes per second of I/O combined. But again, this is not the single job we're running, and it's not unusual that we run multiple jobs at any given time. As a matter of fact, if you look at the other graph, the green one, you see the utilization curve for what we are calling our virtual data center, right? So it's the footprint at Google, and as you see, you have periods that have about 50 nodes, and we go from 50 to 5,000 nodes within 2-3 hours, which, well, I find it's pretty cool. So, to conclude, I would like to reveal some of the opportunities we found, which was the ability to basically use the GPUs that are familiar to us, that provide great performance, and the ability to resize and dynamically create and delete VMs on demand. So we create, as a matter of fact, I think we create usually a few thousands VMs per day, create and delete. That comes with a price of, you have to be obsessed about organizing, monitoring and control your center. But by leveraging these opportunities, we have successfully deployed a virtual data center, what we call a virtual data center at Google, which uses thousands of CPUs and GPUs every day, and do massive seismic processing for production workloads today. Thank you.
You can introduce or no? No? What's that? No, it's okay. I got it. No, I don't need. I click myself. Hey, how you doing, everybody? Everybody can hear me in the back? Mic's okay? Excuse me. Sorry. My name's Adrian Graham. I'm a cloud solutions architect at Google in the Venice office. That's Venice, California, not Venice, Italy, although the food in the office is still pretty good. And I come from a background, a visual effects background. So I spent 20 years as a pipeline TD and as an effects artist at companies like ILM, Digital Domain, Double Negative in London. I worked on some big films. And rendering is one of the big components of working on any film. And that's what we're going to look at today. We're going to look at what a renderer can do in the cloud and what it can do, furthermore, on the GPU. So what does a renderer need? What is the role in the pipeline of somebody who's a renderer or who performs rendering actions is a lighter. And they take all of the assets, all of the massive amounts of data that's generated by modelers and texture artists and animators. And those are simple assets. The complex assets are things like simulation data and complex character rigs and massive environments, like if you have to lay out an entire city, the island of Manhattan could be all completely virtually generated. And what do you do with all that data, and how do you move it around and shift it? So the lighting artist will take all this data and they'll make a beautiful image out of it, and they'll use a renderer. Today we're going to look at a renderer called V-Ray by Chaos Group. But to step back, what does a lighter need to do their job? They need a very powerful workstation, not a laptop. You need multi-core, good GPUs, lots of memory, lots of RAM, and lots of disk storage. All these assets that are generated prior to the lighter getting their hands on them take up massive amounts of space. And that's, as the data's coming in, the data's going out, a lighter is generating frames. We don't render movie files, we render individual frames. 24 frames in a second, that's 24 images, and they could be HD res, they could be 4K, they could be 8K, they could be stereo pairs. Massive amounts are required. You need licensing. You need to be able to license the software on the workstation as well as the render boxes. You need color accuracy so that everybody's seeing the same picture. And of course, you need as many render workers as possible. Now that's the classic description of a lighting pipeline. Today we're going to look at a project by our friend Kevin Margo. Kevin is let me just play these guys. Kevin is a VFX supervisor at Blur Studios in Los Angeles. And Kevin did this short film called Construct, or Construct, however you want to say it. It's about this robot construction worker who shows up on the site one day to find something horrible is going on. You can see it on YouTube. It's a really great short film. But on the right-hand side of your screen, you're seeing the making of. Now, Kevin had he's this visionary director. He's got some pretty interesting ideas about how to do virtual sets and virtual motion capture sessions. And you can see the guy in the suit, this Darren Ross. He is wearing a motion capture suit with points on it that are being tracked by a bunch of cameras. That data is being fed into 3D Studio Max, which is the 3D application, and being rendered in real time by V-Ray. V-Ray RT in this case. In the video, you'll also see Barrus, right, the Siemendorf, who's in the audience today with us. Barrus is the director of V-Ray Cloud and IT at Chaos. Did I get that right? Thanks. There's also some pretty revolutionary cinematography techniques that Kevin has figured out, and that they're using a virtual camera. There's no real-world camera. It's a CG. It's a camera that is simply that rig that you saw with the screen tracked by the director, so that you could really visualize what's going on and what the final result is going to look like. That also means that you're not storing massive amounts of data. You're only storing the positional data for the camera itself. Now, this is the on-set preview that on the right-hand side that you're watching, but on the left-hand side, that's the final render. The final render, in this case, they tried a bunch of different ways to render it. They used CPUs. Each frame took about 2 to 4 hours to render. And they tried GPUs. And this was a couple years ago, so there was, the setups were a lot different, and they didn't have the power that we have on GCP. And those renders took about 18 minutes or so. So what if we could do this on a Google Cloud platform? And let me stop these guys. Well, it just so happens that we can. So before I start, I'm running a remote workstation. I'm not running Windows on my Mac. I'm running a remote workstation in US Central, which is in Iowa, which is about 1,500 miles away, 40 millisecond round trip ping. And this is the full scene that you see there. And I am going to track around a bit and show that, sorry, my mouse wheel is a little bit wonky there. But I'm going to zoom out. This is operating over internet, so it's a little bit slow. But the render is happening almost in real time. And you got to remember how much data is being generated in this scene. Each of these, it's doing geometry substitution on the fly. Each of those red pyramids is being substituted for a full resolution tree. And you could zoom into the forest. You could select a single object and zoom in on it. There's the dumpster. I can go back to, let me just go back to the robots. And the whole idea behind this is not just to move around your scene, but you can change lighting, and you could change animation, and you can change shading qualities. Step back one more. Just want to make this a little smaller so I can see my robots, and there we are. My robots seem to have disappeared, but you guys get the idea. Oh, there we are. Let me just show the entire, these live demos. All right, so I have hosed my demo, but that gave you an idea of what's going on in the cloud. Come see me after I could get it running again. So how did we do this? This is a sort of a little bit more complex for architectural diagram of how we did this, what we're doing right now. for example, we're not doing any asset management database, or we're not syncing our Cloud Directory user database. But we are using something called, we're running over Teradici PCOIP, which is PC over IP, which is a remote desktop protocol developed by a company called Teradici. And you can run this on a piece of hardware. There's this Zero client, which just has a bunch of video outs and an Ethernet port and some USBs. And there's also a software client, which is running what I'm running on my Mac here. There's one for Windows, and there is one for iOS devices as well, which is pretty cool. Boris has it running on his phone. It's not even iOS, it's Android, right? Or it's running in a browser. We are also running a remote machine running 3D Studio Max and a bunch of render instances. The render instances are running Linux, CentOS 7, and as you saw, unfortunately, the interactive remote desktop machine is running Windows. An ancient version, I apologize for that. There's some plugins that I don't want to talk about. And then there's a license server. I'm running a Linux license server that's feeding licenses to both the render instances and the remote desktop. And of course, we're rendering using V-Ray, and those are licensed via the cloud as well. So how do we set all this up? Quite simply, first, we want to create a workstation. And there's 3 important points I want to indicate on this slide here, is that number 1, we choose our zone. And as John said earlier, it's going to be available in a number of different zones. US West is coming up very soon. Had it already been running, we would be running there. The ping time would be much faster. You choose your GPU type. Obviously, we have our K80s right now. And you choose your image. GPUs can attach to an instance running any one of our public images, and you have different flavors of Linux and different flavors of Windows. So that's our remote display workstation. And finally, we want to run an agent, which will allow us to run the Teradici protocol. Then we want to create a render worker, but we want to create the perfect instance that we will then replicate in a managed instance group. So the 2 important points here are 1, they're in the same zone for maximum throughput. And 2, we don't delete the boot disk when the machine goes away, and I'll show you why that is. So you set this machine up perfectly with all the software, the hooks, and the licensing that you need, and then you take it down and you save the disk, and you turn it into an image, which gets turned into a template. The template gets deployed across your managed instance groups. And the final important point here is that you're running a startup script when each of these machines boot. So we want to run the V-Ray standalone server mode, which you could see here runs on a particular open port. And that means that we can take from a list of these servers, these are all the machines that 3D Studio Max is rendering on. And so once the machine boots up, you can use a command to view the serial port output to watch the progress and to troubleshoot. And finally, we launch an entire managed instance group, which is completely dynamic. You could size it up or down. If you want to minimize your costs, you start with only 2 VMs, and then once it's ready, you deploy another 30 of them. And as long as the IPs are all fed into your render options, the renderer will start to expand and run on all these machines. It's unbelievably powerful. So when you think that these frames took 2 to 4 hours on CPUs and 18 minutes on older GPUs that were in a different type of NVIDIA cluster, we're getting almost real-time performance here. Finally, there's some helpful commands that I use all the time to, for example, in this the top section here, I'm tailing the serial port output, and on the bottom, I can view all of my running instances to get an idea of where their IPs are and everything, and to see their status, whether they're being terminated or whether they're coming up or still booting. And that is pretty important when I want to resize my instance groups or stop the entire group entirely. I think we're going to finish off by what John was saying earlier, is that the P100s, which are display capable, are coming soon. Very, very exciting. And the AMD cards as well. I don't know the specifics behind that. But just to summarize what we saw here today, we're running V-Ray RT by Chaos. We're running 3D Studio Max on 128 K80 GPUs. There's 32 instances, each with 4 GPUs, and we're running over TeraDCPC over IP in the software client variant, all running on the single Google Central 1 region. 40 millisecond round trip latency, and it's 1,500 miles away. So all this is happening in the cloud right now. Thank you.
Thanks, Adrian. So let's see, what do we want you to remember from the takeaway? First of all, thank you for everyone that came up and gave a demo, Mapti, Schlumberger, and Adrian from Google, showing how V-Ray works with 128 K80s running at the same time. So fantastic and fun demos. And I guess what I want you to remember is if you want performance that's scalable, and come to Google Cloud and fire up a bunch of GPUs. And thanks for coming.